We'll take a look at some problems that I have written out. So let's see. Okay, here's one that we can do. I'm pulling some out that I already have written down. Looks like I don't have too many written down, so maybe we'll just have to troll the book for questions. Oh, here's one. So actually, these are some that I've done before, but I'm going to just do them again. It's not too bad. And I'm going to do this extra one. Okay, so I'm going to change my share here. And you should be seeing my tabletop now.
Yeah, I do.
And here, number 8 is one of the ones that you're curious about, the lanthanides. They're kind of, down below, right?
Yes.
And here's how I go about getting those. So for A, let's see, am I recording this? Pause recording. Yep, must be recording. So we're going to look at samarium. And if we look at this in the periodic table, we'll see that it is right here, number 62. Okay, so to start with this one, you look at the number 62 and you find the noble gas that is closest to samarium, but has a smaller atomic number.
Xenon?
So basically I say you find the noble gas before samarium. And can you see that xenon is 54, radon is 86, so we want to go with xenon because it's below samarium, which is 62?
Yes.
So that's where we're going to start. And then what I'm going to do here is I'm going to draw the periodic table so that it will help us out. So this is 1, 2, 3, 4, 5, 6, 7 for the periods. And then down here, this is actually part of period 6, and this is part of period 7. Okay. So I'm also going to label these as 1s, 2p, 3d, and 4f. And the reason I label those is because I now know that below 1s is 2s, and then 3s and 4s all the way to 7s, okay?
Right.
And what's below 2p is 3p, right?
Yeah.
And what's below 3d is 4d, and so forth and so on.
Right. With
So,
helium 1s still.
right, so xenon is right here. So I'm not sure, can you see xenon on the,
Yeah.
okay, good. All right, so if we look at xenon and we go to the next block, it's going to be the 6s, and you're going to write 6s2, because to get to samarium, it's down here.
Right.
Okay, now if you look at the periodic table, which I'm going to bring back and cover this up, what we've just done is we did xenon and we picked cesium and barium. That's 6s2, right?
Right.
Now, do you see lanthanum number 57 is here in the D block, 3D, 4D, 5D. So lanthanum is actually 5D1.
Okay.
And then from 57, we don't go to 58 next door. We have to go to 58 down below, and it starts with cerium. So I'm going to go ahead and write down the 5D1. And now we're going down below. And if we go down below, do you see how the top row is called 4F and the bottom one is 5F?
Right.
So what we're going to do is we're going to call these 4F down below here, and we're going to count 1, 2, 3, 4, 5. So we're going to say 4F5. But we're not done. What we're actually going to do is change this to xenon 4F5, 5D1, and 6S2, because you want to write them in increasing shell number. So 4s go first, then 5s, then 6s. And this would be the noble gas SPDF notation. Here's the noble gas part. Here's the SPDF notation.
Can you show me the periodic table in the book one more time down there?
Yeah.
I'm just using a printout, and I think they may have started the lanthanides and actinides on the wrong one.
The printout you're using probably has lanthanide down here and actinide down here, right?
Right.
They're not part of that block.
Right. They're different.
Right. They actually belong up here, and you may have blank spots here. Is that the case?
I do. Yeah.
Okay. Well, you have to remember that lanthanum belongs up here, and so does actinium.
Okay.
Because this F block is supposed to be 14 elements long. And if you include lanthanum, it's 15 elements.
So the lanthanum is a 5D and actinium's a 6D?
Correct.
Okay.
And the reason your periodic table puts lanthanum down here and actinium down here is because the elements that follow are named after lanthanum and named after actinium. This whole row of elements are called the lanthanides because they follow lanthanium.
Mm.
And these are called the actinides because they follow actinium.
Okay. So that's why I was confused why there was 5D1.
Okay, so that's why it's 5D1. Lanthanum is actually a 5D element.
Okay.
And actinium is actually a 6D element. So here I can write this. Cerium is where it begins, and thorium is where it begins. And here's lanthanum, and here's actinium. Okay, so let's try this for ytterbium. So using your periodic table, where is ytterbium?
It's the last lanthanoid.
Okay. The last or second to last?
It's the last one. The next one.
Okay, your periodic table is also messed up there because it should be YB
Just
here
cut off a different one.
and then LU here.
It's funny, I've been using this all semester.
Okay, so here's YB and here's LU.
Okay.
So LU is the last one. And how do you know that LU is the last one? What is the element right here? It's hafnium, and that's number 72. And I bet your periodic table has hafnium up here. Is that right?
It does. So then lawrencium is next to nobelium.
Right. And
Okay.
that's down below.
Okay.
Where does your periodic table have lutetium? Lutetium, L-U-T. If ytterbium is the last one, where is lutetium?
It's what I thought was the first 5D.
Oh, they put it up here on the 5D?
Yeah.
You're kidding me.
Uh-uh.
Yeah, don't use that periodic table. Someone just really messed that one up. Someone who didn't understand chemistry at all just said, well, you know what? These are the lanthanides, so of course they have to start with lanthanum.
Mm.
And then they just screwed up from there.
Right, it just kept getting worse.
So if you really want to see a decent periodic table, your book has one.
Right, I printed it off because I have the online book and it's hard for me to look at it online.
Do you know where you did? Is it? That's not the one that I put on the exams or quizzes, is it?
No.
So let me do a new share here. So now you should see my browser.
You know what? At the top of the paper, it says webelements.com. So it's just the printable version of that, however they made that.
Okay, then Web Elements screwed it up. Let me take a look at Web Elements here. So yeah, they have lutetium right here to begin with, and that's bad.
Write them a letter.
Well, they're English, so you have to forgive them. They're a little hoity-toity. So if we go to periodic table, just typing that into a search and go to images. I usually don't like all of these ones that have all the different colors. Too busy. Do you see this one right here that I'm going to click on?
Yeah.
So this one I also don't like because lanthanum and actinium are down below.
Right.
So we're going to pass on that.
At least they got lutetium and lawrencium though.
Yes, they did. Let's take a look at this one here. Here they have lanthanum and actinium in the wrong place. So I'm going to pass on that. Look at this one. This one, you can see that they're trying to point out to you that cerium follows lanthanum and lutetium is at the end here. Thorium is at the beginning and lawrencium's at the end. So this is a pretty good one.
Okay.
Now this is one I wouldn't put on your exam because it gives you way too much information, like the name and all of that.
Right.
And there's even one that you can find online. Let's see, periodic table, Word document, free. Let's see if, I think there's one that's a Word document someone made. What's going on with my search? That wasn't a tough search. Oh, it was just getting hung up. So here, if you take a look, apparently these are Word documents. And I'll just go to this very first one. And this very first one, if we view the image, well, this one kind of sucks because of the resolution. But it started with cerium, so I like that.
Right. So I just need to find one that has the right orientation of those.
Yeah. Here's another one. This has the names on it. But apparently this first one that I went to, if you go to the page, apparently you can download it. Free. Log in to download. I'm not going to log in. I don't even have an account there. Okay, but at any rate, you can see what you can get there. So that may solve all of your problems. So here's ytterbium right here. What are you going to write for the electron configuration?
Well, I'm going to want to do xenon.
Okay.
6s2, 5d1.
Okay.
4f, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Okay, now you don't need to count because you know that it's 14 wide, right?
Okay, yeah.
So it's the second to last one. It's got to be 13.
Okay.
And then what do you do?
I would do 4f13, 5d1, 6s2.
And that's how you do it.
Okay.
So that's number 8. Let's do number 9 or number 10. So here we're looking at plutonium. Plutonium is right here. It's below samarium.
Okay.
So this is going to be number 10A, plutonium.
So radon, maybe 7s2, 5d1, 6d5.
6 what?
6f5.
Yes. And then what are you going to do here?
5d1, 6f5,
Okay.
7s2.
But I think this is pretty good except for one issue.
Let me see where. S 7s.
Is it a 5D or is it a 6D?
Oh, it's a 6d because it's actinium.
Okay, and there's another issue. Is it a 6F or is it a 5F?
It's a 5f.
It's a 5F.
Okay.
Okay, so I'm going to cross that all off again and read it to me again as if you were doing it for the first time.
It would be radon, 7s2.
Now, how do you know it's a 7 instead of a 5?
For S because it starts after radium. Or
Well,
will
I would say that when you're looking at the periodic table, it's 1, 2, 3, 4, 5, 6, 7. That's how you know it's 7.
okay, 7th period.
How do you know what this one is? Actinium. What's actinium?
6D,
How do you know it's 6D?
because it comes before Rutherfordium.
Actually, I would say 3D, 4D, 5D, 6D.
Okay. Okay.
So each of these blocks starts as follows: 1s, 1,
Right. 2P.
2p, 2, 3d, 3, 4f, 4.
Okay.
So they start with 1, 2, 3, 4. So how do we know plutonium is 5f? And the answer is because it starts at the top with 4f, then becomes 5f.
Right. Okay. Because you just count down.
Right. So here, my little fake periodic table, is very useful, but if we're not looking at it, then we might have problems.
Okay, so xenon for plutonium, it's xenon in brackets 7s2.
Hold it. For plutonium, it's radon, right?
Oh yeah, right on.
Okay, 7s2 then.
Then 6d1,
Good.
and then 5f5.
Okay, and then we rearrange this and what do we get?
5f5, 61, 7s2.
Okay. So radon, 5f5, 6d1, and 7s2. Well, what about Rutherfordium? That's not one of the questions, but what about Rutherfordium? That's right next to actinium. What would that be?
That is a 6d1.
Well, don't we want to start with radon?
Yeah.
And then isn't it 7s2?
So right on 6d1, 7s2.
Well, we don't want to jump ahead. Let's
7s,
read it off the periodic table.
right on 7s2,
But you
6d1.
see how we have to get to Rutherfordium? We have to do a 7s2.
Right.
And then we are going to do a what? Is this a 5D or 6D or what is that?
A 6d.
Okay, 3, 4, 5, 6D. How far over in the D's is it?
2.
So 5D2, and actually 6D, not 5D, 6D, right?
Yeah.
And then actually to get to the second D, as it were, don't we have to go from 89 to 104 down below?
Right.
So we have to go through this whole bottom row. What is this whole bottom row?
5f14.
That's right. We don't even need to count because we know it's 14 wide.
Okay.
So when we rearrange this, we get radon, 5f14, 6d2, 7s2. How about curium? So curium is, let's see, where is it?
Um, 96.
Okay, there you go, 96. So what would curium be looking at our periodic table?
Radon,
Okay, radon.
7s2,
Okay,
5d1,
how do you know it's 5D1?
because we're not going past that. We need to jump down.
Okay, so let me back it up then. If this is curium right here, we are going through 7s2, right?
Right.
Now, how do you know which subshell this is?
Because it starts at 3, 4,
Okay,
5,
so
6.
why don't you go ahead and count and see what it should be?
6d.
6, not 5, 6D. Okay, and what does this top one supposed to be?
4f.
So what's this bottom one?
5f.
So 5F what?
5f. 7.
5F7. So that's what we get. But we have to rearrange, and we get radon, 5F7, 6D1, and 7S2 for curium.
Okay.
And you probably can't see that very well because I need to zoom a little. Okay. So I can see that we're having a little bit of trouble with the D's and the F's as far as what the number is for that particular row.
Right.
So what you probably want to do is take the time to maybe make some blank periodic tables that look like this.
Right. Just so I can remember which coefficient to put in front.
Yeah, and when you make these, what you do is you go 1S, 2S, 3S, 4S, 5S. You don't really have a problem with this one, do you?
No, that's why I was asking about the ones, the lanthanoids and actinoids, but I guess all the ones around it too, I struggle with.
Now, you don't seem to have a problem with these either, but I
Right.
don't know. But here you might want to just go 3D, 4D, 5D, 6D, and then do it again. 3D, 4D, 5D, 6D. And then down here, go 4F, 5F, 4F, 5F. You can probably just make one periodic table and just do it again and again and again.
Right.
So you want to get into the habit of thinking about what row, what number belongs with what row. And this one is weird, admittedly, because this is the 4th period, but that's the 3D subshell.
Right.
Okay, let's try some more here. So here's number 12. Oh, this is not a good one. Here's number 46, element 109, now named meitnerium, was produced in Germany. What is the electron configuration using SPDF and noble gas?
Okay.
And name another element found in the same group as meitnerium. So we're looking at element 109, and in the periodic table, let's see where that is.
In the 7th.
It's right here.
So it would have radon 2.
Radon would precede it, and then what would you have?
7s2.
Okay,
Where are we here? 6d7.
right. 1, 2, 3, 4, 5, 6, 7. So 6d7. And how did we get from 89 to 104?
I mean, I just counted the,
Actually, what I'm asking is, you did 89 to 89, and then you did 104 to 109. What about 90 through 103? Where are they?
well, you need to add up to 109.
You do. So let's see if they add up to 109. So what you have so far is radon, 7s2, and 6d7, correct?
Right.
Radon has 86, 7s2 has 2, 6s7 has 7, and that adds up to 95, not 109.
Okay.
So if you look at the 109 and the 95, you're missing 14. Which 14 are you missing?
5F14.
5F14. So you got to remember here that when you're going from here to here, you actually have to read it off the periodic table. And the way you might read this, if you did it in order, would be 7s2, 6d1. So I'm going to write that down. Radon,
Oh, and then you do
7s2, 6d1. And then after your 6d1, you have to jump below and start at 90 and go all the way across and say 5F14.
And then put a 66 at the end.
And then another 6d6 because you have 6 more to go through.
Okay.
But we don't need to do that. We can just see that in the D's, we have to go over 7. But you have to remember that in the D's, when you go over past the first one, you still have to go down and catch the ones below.
Right.
Okay, so that's why I say we don't need to do this, because if we did do this, we would rewrite it as follows: radon, 5F14, 6D, and we're not going to write 6D1, 6D6.
Just 67.
We're going to write 6D7 and 7S2.
Okay.
So you missed that 14 because you kind of forgot that, you know what, only the first element of the D block is filled, if you will, before you go drop down into the Fs.
So really anything in period 6 and 7 past that, you have to remember to account for the lanthanoids and actinoids when you're writing it in this notation.
Anything past lanthanum, anything past actinium is going to have an F,
Right.
either a 4F or a 5F.
Okay.
Okay.
Yeah.
So you think you got it?
I'm going to need to practice more, but yeah.
Okay. Now what you can do to practice is you can actually do all of those elements and you can check your work. So let's practice with one and then we'll check our work. And we're probably going to find out that we got it wrong, but that's all right. So let's take a look at one that I think will be wrong. Let's do americium.
Okay.
So americium is number 95.
So
what are we going to start with for americium?
radon.
We'll start with radon. And what comes next?
7s2.
Excellent. And what comes next?
6d1.
Okay.
5F14. 6.
1, 2, 3, 4, 5, 6. So 5F6. Okay, and then we rearrange, and what do we get?
5F6, 6D1, 7S2.
Okay, radon. 5F6, 6D1, and 7S2. And let's see if we're close. Now, this one here, this element, americium, has 95 electrons, right?
Right.
So it turns out that our book actually shows you all of the answers.
And you can check by counting at the end and know fairly.
Oh, yeah. You can check to make sure you have the right number of electrons, but we're looking at number 95, and look at what it says. 5F7, 7S2.
5F7.
5F7, 7S2, not 5F6, 6D1, 7S2. So this is the SPDF method that we learned, right?
Right.
And this is the real electron configuration.
Okay.
Now, on an exam, I expect you to get the one above, not the one below.
Okay.
Okay, but let's try to understand, did we do so badly? And the answer is we only have one electron out of 95 that we misidentified from reality. You with me?
The 60 moved to the F.
Moved to the 5F, right?
Right.
And so that means that 94 out of 95 electrons are correct.
Right.
So that means we're about 99% correct.
Okay.
So the way to look at these two is not to say, you know what, we screwed this one up. We're supposed to say, you know what, it's 99% correct. Now, I do want you to understand why they're different. So I'm going to take this radon, the one that we got. So this is the SPDF. And I'm going to write this out this way. And I'm going to use the what's called the noble gas orbital box diagram. So an F orbital has 7, or an F subshell has 7 orbitals. So each box is an orbital. A D subshell has 5 orbitals. And an S subshell has 1 orbital. Now, when we put these electrons in here, you're supposed to put 1 electron per orbital. And then if you run out of space, you pair them up.
Right.
So you see for the 7s, we put 1 electron in there and we've run out of space. So we had to put the next one in there and pair it. So this is what this would look like. Now, the reality is the following. You might be wondering, why does he always put the middle one in first? And the answer is, if I put the middle one in first, I know how many I need to the left and the right, and it's easier for me to space it out.
I just added a box on the end instead.
Oh, so this is 5F, right? And we have 7 of them.
Okay.
There's no 6D, and then there's the 7S. Okay, so here's what's going on here. If you take a look at all of this right here, and you have to remember that each subshell is a sphere, okay?
Okay.
Each subshell is a sphere. And each of these boxes is a little small portion of that sphere, okay? In this case, the box is the full sphere. So in this case, these two are exactly identical, so they don't really influence things. But let's take a look at the 5F and 6D versus just the 5F. So here, can you see with this 5F, there's this little orbital here with no electrons in it.
Right.
And here with this 6D, there's one orbital with one electron in it. And so the deal is here is that you're kind of shoving the electrons into a small space and not letting them spread out. And why would you want them to spread out? The answer is simple. Electrons are all negative. They repel one another. So to spread them out into space is a little better than to confine them into less space. So here with these 7, you're spreading them out more evenly than you are up here. You could actually argue that the amount of space you're combining these into is the same as here. But here, it's not quite the same because it's not evenly distributed.
So you could say that like the D orbit is like almost within the F.
Oh, these all overlap. They all overlap. But here, when you're putting them all in this 5F subshell, the electrons can evenly distribute themselves. And that's the best case scenario when the electrons repel one another. You don't want to put 2 electrons too close together.
Right. They just want to go to the path of least resistance at that point.
Right.
Okay.
And when you have different types of orbitals here, you're not able to evenly distribute the charge. And so it's not as healthy.
Okay. So in actuality, it is the one underneath.
So this is the real one. And the reason it is this one is because the electrons are more symmetrically distributed, resulting in less repulsion and more stability. So that's the reason for it. They call it the symmetry argument, but you really want to know the background of the symmetry argument. The background of the symmetry argument is that you're going to end up with less repulsion and more stability.
Okay.
Okay, so let's try something else. You're like an experiment for me. I'm going to give you an electron configuration, and I want to know 3 things. 1, what is the element? 2, what is the SPDF electron configuration? So that means using that SPDF method.
Okay.
Where we read it off the periodic table. And then why are they different? Okay, so remember, I'm not going to tell you what element this is. I'm just going to give you the electron configuration. So that means I have to find one that the book gives us that I know is wrong. Did we do nobelium? Oh, wait, I just told you what it was. That's no fair. Skip that. Well, shoot, I'm going to do it anyways because it's easy to tell what it is. So Rn 5F14 7S2. So what element is it?
Radon 5F14. 7s2. I'm wondering if when I count, I want to say that it's the one after nobelium, but you just told me nobelium.
Well, how many electrons are in radon?
86.
Okay. How many are in 5F14?
14.
14. Okay, now say it like you mean it. How many are in 5F14?
14.
Okay, say it like you really mean it.
Okay, so it adds up to 102, so it's nobelium.
Okay, so I just want you to be sure that you know that this number up top is the number of electrons.
Right.
So this adds up to 102. So that means the atomic number is 102, which means it's nobelium. Fair enough?
Right.
Now, why did you want to pick the one after nobelium?
Well, because that's the 14th F.
And that's not how you do it. So what did you just learn about figuring out what element it is? Don't say, oh, it's the last one in the 5F. Don't do that. What do you do instead?
Add up the electrons.
Count electrons.
Okay.
And then find the Z with the same number with the same number, right?
Right. Okay.
So count electrons, then find the Z with that number,
Right.
or find the element with that atomic number.
Oh, so really these ones are pretty easy then.
Oh, they're really easy as
I'm
long as you can
way
count.
too hard about it.
Yeah, you don't need to figure out, you don't need to say, okay, so if it's a 5F14, but it's you don't need to do any of that.
I just need to add up the superscripts and find radon and.
Yes, you need to know how many electrons radon has.
Okay.
And then you have to figure out how to add that to 14 and 2. Okay, B, what would we get for the electron configuration of nobelium? So let's see, nobelium is right, 102, right?
Yeah, I would do radon.
So it's
7.
right over here.
Yeah.
So go ahead and tell me what you think it is.
Radon 7s2 5f13.
No. Seven S2, yes. What happened to 89?
Oh no. I still need to add the 5d61. 61.
Correct. Okay, so we would expect it to be radon 7s2 6d1.
Oh, to account for the other electron. Okay, and then 5f13.
Okay, and here's where you would have discovered your mistake. You would have checked your work. You would have added these up together, and maybe you don't even need to add these together because you know that this is 86 plus 2 plus 13. When you add up two evens and an odd, you get an odd total, right?
Right.
So you know this is wrong. And you have to, where is that other electron? And you would have been going back here, going across, and you would have said, oh, I forgot actinium. So that's a 6d1. You almost made that mistake of calling it a 5d, right?
Mm-hmm.
Okay, so what would this be called, rewritten as? Radon 5f13 6d1 7s2. Now, why is the real electron configuration more stable than this one?
Because there's less repulsion.
Yeah, we're going to say the electrons are distributed what?
More evenly, maybe.
More evenly.
They don't have extra pressure on them from the other orbitals.
So resulting in less repulsion, making them more what?
Stable.
There you go. So it's kind of like a three-part answer.
Okay.
Evenly, less repulsion, more stable. Okay. So I can see that you're going to have to fine tune this a bit.
Oh, yeah.
And don't be afraid to do the SPDF method and then compare it to the ones that the book gives you. And remember, if they're different, you want to know the reason why. And what is the reason why?
The reason why is because there is less repulsion and more stability.
They're more evenly distributed,
They're,
right?
okay, the electrons are more evenly distributed, so there's less repulsion, resulting in more stability.
Right.
Okay.
And hopefully that's the reason why they're different, not because you screwed up.
Right. Right.
So you want to practice a few of those lanthanides and actinides. And there are, most of them are what we would predict, but a few of them are different.
Right. And normally it would be different by one, probably.
One electron. I think there's a couple that are different by 2 electrons, but most
Okay.
of them are different only by 1 electron.
Okay.
Yep. Was there something else you wanted to cover?
I guess maybe the orbital boxes with the arrows up and down for the spin.
Okay.
When you
What
were
you mean, like
like
what?
diamagnetic and paramagnetic stuff.
Okay. So we can actually take a look at one of the ones that we did here. So do you see this? This is americium, and this is the real one versus the one that we got.
Right.
It doesn't matter which one we use. This would be called paramagnetic.
Right. If it's only diamagnetic if all of the electrons are there.
Right.
Okay.
Let me ask you this. Where on the periodic table are you likely to find diamagnetic elements?
The rare gases.
Yes. Where else?
Alkaline, maybe? I just know that when I went through it, I found that
Alkaline earth metals, right?
Yeah.
Also, another place you're likely to find them. You already said the noble gases, and you're correct. Some of these guys. Why some of these guys? Well, let's take a look at this guy right here. That guy is zinc. So zinc would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. We would rearrange this and write it as 1s2, 2s2, 2p6, 3s2. And a good question right now is, why didn't he start with the noble gas? And the answer is because I wanted you to see every subshell. So this is zinc.
Right.
When we look at this 1s subshell, there's 2 electrons in it.
Right.
When we look at the 2s, there's 2 electrons in it. When you look at the 2p, there's 6 electrons in it.
And is that right there argon?
This would be neon.
Okay.
Argon would be this. Whoops, I made a mistake. That's supposed to be 3s. 3p. So that would be argon right there.
Okay.
And then we have this 4s. Actually, my mistake, that would not be argon. And I forgot my 3d10.
So does argon end at 3p6? Or
Yep.
does it? Okay.
So here I got to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then my 4s.
So the difference is 3d10, 4s2?
Yeah, that's the difference. Now
Okay.
notice every subshell is full. So what does that mean about every electron? It's paired with another one. So this is diamagnetic.
Okay.
So that's going to happen for all of these. And even these down here, when you look at this guy right here, what is that element? Let's find out. That one is copernicium. So copernicium is number 112. And its electron configuration would be radon. So copernicium, Cn, would be radon. (7s2), and then we have to go all the way across the D's, so that would be, here's copernicium. So I got 7s2, then what would we write down for all of this?
6d15?
No.
I need
1,
I
2,
think-
3, 4, 5, 6, 7, 8, 9, 10.
Oh, right. I wasn't thinking till you get to 112.
So you'd say 6d10, right?
Right.
But to get to 89 to 104, we have to go down below, right?
To 5f14.
Okay, so 5f14. Are all of these subshells full?
Yes.
Okay, so what does that mean about all their electrons?
They have pairs and
They're paired, so what does that mean about their magnetism?
diamagnetic.
Diamagnetic. So the ones that are paramagnetic are really easy to pick out. All you do is look at the electron configuration. If the subshell isn't full, you have to have an unpaired one. Like for instance, carbon. Carbon has 6 electrons, 1s2, 2s2, 2p2. Now, when you look at it, you go, oh, they're all paired because it's 2, 2, and 2. But that's not so. Here's what the 1s looks like. Here's what the 2s looks like. And here's what the T2p looks like. Notice that we do not pair the electrons together.
Right.
Hund's rule says when you're putting electrons in here, put them in the more stable subshell first. But for a particular subshell, if there's more than one orbital, put 1 electron per orbital before pairing them.
Right.
And the reason we do not do this is pretty much for the same reason as that symmetry argument. Why would you put 2 electrons in the same orbital when they repel one another?
Right.
Wouldn't it be better to put them in different orbitals?
Right.
So if we draw these orbitals, here's one of them, here's another one, and here's the Z orbital. It's really complicated looking. I'm going to redraw this and just draw the X and the Y orbitals, right?
Okay.
So we'll leave the Z off because the Z, there's nothing in there.
Right.
So I'm going to redraw this up here without the Z. Here, in this case, we put one electron here and one electron here. Here, we put them both here. Which is going to be more stable, putting one electron per orbital and let them spread out, or both electrons in one orbital and let them fight it out?
When they're spread out, it will be more stable.
This will be more stable. And so you can see that the reason the real ones are different is just kind of an extension of Hund's rule, which says, you know what, spread them out.
Okay.
Okay, so you don't want to look just at the superscript and say, is it even or odd? You really want to look at the superscript and say, is that subshell full?
Right.
Because if it's full, they're all paired. And if they're all paired, it's diamagnetic.
Okay.
And that's actually a rare thing, not a common thing. So that's kind of a weird thing to think about that. Diamagnetic means repelled by a magnet. Paramagnetic means attracted to a magnet. So most elements are attracted to a magnet. And that's not the way we usually think of elements is, oh, everything's attracted to magnets.
I would think iron.
Iron is attracted to magnets, yes. But on the other hand, just because something is attracted to magnets doesn't mean that it's greatly attracted to magnets.
Okay.
Okay, so you can't really define how attracted it is based on unpaired electrons. It doesn't work that way. So that's why the book doesn't ask you any questions about that, like which one of these is more attracted to a magnet, because it's a different idea. Okay.
Yep.
So does that help you with the orbital box diagram?
It does, yeah.
Okay. So you follow Hund's rule, you put them in the more stable orbitals first. And when you have a subshell with multiple orbitals, you put one per before you pair them.
Okay.
All right. Well, it's 7:09. It's time to call it quits.
All right. That was informative.
Good. I hope you have some stuff that you can think about and, apply it and give it a shot.
Okay. Thank you, Tony.
You bet. Have a good evening.
You too.